Hey everybody. So here we are with the section 4.3. Okay, so section 4.1 was about exponents, exponential functions. Section 4.2 introduced that function's inverse, which is logarithms. Then we went back in time to section 3.7, which talked about variation, and now we are already at the fourth section. And these are just one day apiece, so that should be encouraging, I would think, since if it can all be covered in one day, then not too much material is required. But I very much hope that you're keeping up on your homework. Okay, so properties. You remember from exponents, if you multiply two powers that have the same base, then you just add the exponents. We looked at that a little bit. Logarithms are really exponents because logarithms produce the exponent that would go on the base that gets you to the power. So if it should be a big surprise to realize that when we add logarithms of the same base, you can think of it as adding exponents that are both attached to this base. And since when we added exponents, that was the result of multiplying the powers, then the logarithm, these two logs will join to become one logarithm, but the power will be negative 6x. And that's from 3x times negative 2x. So in short, if you are adding two logarithms that have the same base, then you can make it as one logarithm, but you multiply the two powers. So log base 7 of negative 6x. Okay, so in general, m and n, we're told that they're greater than 0, which they would absolutely have to be since logs can only receive positive numbers here. And when you're adding two logs that have the same base, you just write it as one log. You multiply the two arguments, m and n. Some common things that could go wrong, these I see a lot. First of all, multiplying two logs, you hardly ever do that. That's a very, very uncommon thing to do. So just the, these two right here, if you add these two logarithms, it does not equal the logarithm of the sum of the two arguments. You multiply m and n, you don't add them. And then the problem with the third one here is that it's just this 3. This 3 out here is only influencing this first log, not the second logarithm. So you can't really combine them just yet because you've got 3 of these and only 1 of these. So it does not combine to this, nor does it make m plus n in any case. So these are all common things we want to avoid. If you're adding two logs that have the same base, you can write it as one log with that base. You just multiply the two arguments that are inside. And as an extension of that rule, which is really just a redundancy, is the power rule. So we know with exponents, this was a redundancy too. X to the m to the n is just x to the m n amount of times. So you end up adding all of these m's, and there happen to be n of them. So when you're adding an n group of m's, you're multiplying. So this is the shortcut with the power rule is a power to a power, you multiply those two exponents. Similarly with logs. So here I've got a log base 3 of x to the fourth. So that is the same, that's the same thing as log base 3 of x times x times x times x, right? But that's the same thing as log base 3 of x plus log base 3 of x, plus etc. So I'm referring to that last slide that we just talked about. If I'm adding two logs, then I just multiply the two arguments. Well, I can put that in reverse. If I have one logarithm, that's m times n, I can separate into two logs just by adding them. So here I've got one logarithm with x times x times x times x. I could separate it into 4 unique logarithms. They all have the same base, but I have 4 terms that are identical. That means I've got 4 log base 3x. And the shortcut, of course, is this. If you have log base 3 of x to the fourth, that little 4 as an exponent can just jump right into the front of the logarithm. And here it is in a more abstract form. So log of any positive base of m to the n will equal this. You just take that n, you put it in front, it acts as the coefficient. This is a very common mistake. What's the problem here? How come this isn't true? Because the 3 is only affecting the y. It's only y to the third, not x to the third. This is x to the first power times y to the third power. But this 3 times this log, which has x and y, this would mean that both x and y are being raised to the third. So they are not equal. The quotient rule with exponents, when you divide powers, you subtract the exponents. Same thing here. If you subtract the exponents, so you subtract the logs, you would divide the powers. So 3x divided by 2x plus 1. Be careful here because subtraction and division are not commutative. So order does matter. Whatever comes first is the numerator. And some common mistakes. I don't think anyone would do this, but if you subtract two logs, it doesn't mean you subtract the m and the n. It's not really, I don't really see the mistake going from left to right. I see this mistake going from right to left. People are faced with m minus n, and they're very, very tempted to separate it into two logs that themselves are being subtracted. That would be like distributing the log, but that's total nonsense. We don't distribute operations. We distribute numbers and we distribute variables, but logarithm is a function. We're not going to distribute that. Let's practice. There's two, looking at the homework, there's really two things that are required of us. We need to condense all these logarithms. So we have a bunch of logarithms. Can we get them down? Can we squeeze them down into just one logarithm? And then can we reverse that? Can we take one logarithm and expand it as much as possible? Well, to condense them, first of all, I see this plus sign, so I'm going to multiply the arguments x and y. But first, it's not just y, there's a 3 in front. So what does this 3 do? This 3 is going to become the exponent on y. So it's log base 10 of y to the third. And now I've got this 1 log plus 1 log. Now I can combine both of these by multiplying the two powers. X times y to the third is log base 10 of x times y to the third. Whoops. Here we go. This one, you're subtracting two logarithms. So subtraction implies division here. Notice the coefficients are 1 and 1, so I've got no problem like I had this first one. So I just simply divide the two arguments, x minus 7 over x. It is not this. Dividing by 4, that's the same thing as 1/4 times all of that, which means the 1/4 could act as an exponent on x minus 7. So this is not correct and should be avoided. The arguments, or the domain, the specific domain of the two logs, those get divided, and only those. And once you divide them, they are part of the new logarithm. All right, this one's a doozy. Probably pause it and see what you would do to continue. This is already, this 9 has drooped down. Okay, so it's 1/3 times, see the brackets? 1/3 times all of this plus this. Notice it's all log base 2. Thank goodness. Well, the first thing I could do is 1/3 is just a number, and I've got two terms that are being added. So I could just distribute 1/3, and that's what I'll do. So that becomes 1/3 times this logarithm. Oh, there's that 9 again that swooped down. And then 1/3 times 2 becomes 2/3 times this. And this third logarithm did not change. Well, now what? Before I can combine all three of these by the addition rule, like if I add these two, I can just multiply the two arguments. Before I do that, I have to get rid of these coefficients. So what does this 1/3 coefficient do? it makes 9x raised to the 1/3. And this 2/3 makes x minus 2 raised to the 2/3. And that is cube roots. Something raised to the 1/3 is the cubed root of that thing. And something raised to the 2/3 is the cube root of that thing squared. Now I'm finally ready for my last step. 2 more steps, it looks like. You are adding these two logarithms, so I can just make them one logarithm, and I get to multiply them. Luckily for me, I can group them all under the cubed root because these are both cube roots, so I get to combine those. They're kind of like terms in a way. And then finally adding this. Notice this x is not the cubed root of x, so it's going to be outside of the cubed root operator. And this is our final answer. Log base 2 of x times the cubed root of 9x times x minus 2 squared. It's a real mouthful. And then reversing it. If you have one logarithm, can you untangle it to create multiple logarithms? Here we've got log base 8 of 21. At first, it doesn't look like there's much we could do until we realize that 21 is the same thing as 3 times 7. And if I'm multiplying two things, then I can separate the logs. Log base 8 of 3 plus log base 8 of 7. And this is about as far as I can go. Here, you're dividing. So you could separate it right away. We could separate it into two logs. Log base e, which is the natural log of e to the 4th, minus natural log of 8. Natural log of e to the 4th minus natural log of 8. What else could I possibly do? I guess you could separate the 8 into 2 and 4, but I don't know. We're not going to do that. What we can do here, though, we can do something. This we can actually evaluate in our head. Logarithms are exponents. So what is the exponent that would go on e that would result in e to the 4th? And that number is 4. So this is a great answer, a great stopping point. 4 minus the natural log of 8. 2 more. I've got a division, so right away I'm subtracting. I'm going to separate this into two logs. Log base 5 of 25 minus log base 5 of this. Well, hold on a second. Log base 5 of 25, 5 and 25 are related exponentially, right? 5 squared is 25. So this logarithm is 2. Now this one, what can I do? Well, 2 minus x is, I'm taking the square root of that. Well, can I write that square root as an exponent? Yeah, that's 2 minus x raised to the 1/2. And now that I've got an exponent, I can take this and swing it out in front, giving me the final answer of 2 minus a half times log base 5 of 2 minus x. And our final problem here, again, a big division. So I'm going to start with that and separate it into two logarithms. Hello. Natural log of the numerator minus the natural log of the denominator. And I can separate this. The first logarithm has x to the 4th times the square root, so I get to break that up into a natural log plus a natural log. And I've got this 4 as an exponent. I can swing that 4 to the front. There's also this 5, which I could have done after this step, but this 5 can also go into the front. And also notice what I did. The square root is the same thing as raising it to the 1/2. And so the last thing I could really do is bring that 1/2 over. And that is done. There's really nothing else I could do. You may be tempted to break this up into log of x plus log of 3, but that is dead wrong. There's really no sufficient way to break these two logarithms up anymore.